Hello, everyone. Good afternoon, good day, or maybe good night to all of you. Here is webinar number 6, AM Smart, about advanced manufacturing of smart materials structures. We have another session about shape memory materials as a main focus, and this session will be hosted with Professor Dermot Brabazon from DCU University in Ireland. We have two nice speakers here, Dr. Burkhard from ING Pulse, Germany, and also we have Dr. Marialaura Tocci from University of Brescia. And it's already mentioned and advertised earlier about the topic of their presentation. The first presenter is going to talk about customization of NiTi shape memory alloys for elastocaloric application. And the second speaker will talk about effect of direct aging heat treatment on superelasticity of nitinol proceed with L-PBF process. I hope you enjoy with both talk today. Yeah, thank you very much, and Professor Brabazon.
Thanks very much for the organizing and putting together of these webinars, firstly. So thank you for doing this. Our two presenters today, Burkhard Maaß and Marialaura Tocci. Burkhard Maaß is going to talk on the electrocalorific aspects of development for shape memory alloys, so nickel titanium based alloys for elastocalorific application. And Marialaura is going to present on the superelastic nature of nickel titanium for applications in the biomedical space, and how the processing of that achieves the properties required for stent applications in particular. So without further ado, I think we should kick off with the first presentation. So Burkhard Maaß, the CEO of Ingpuls, is going to present the first presentation. So I'll pass over to Burkhard.
All right, thank you for the introduction. So I'll start by sharing my screen. Oh, you should see my screen right now.
Yeah.
Right, so the work that I'll present today is some of the results of our group on the customization of NiTi XY, because mostly I talk about quaternary alloys, shape memory alloys for elastocaloric applications, where I focus less on the applications and more on the material properties. Most of the work has been done of the experimental work by my colleague Alexander, who's also here in the webinar, and we share discussions and ideas on what to test for, and we rely heavily on feedback from the elastocaloric community. People like the group of Paul Motzki and Stefan Seelecke, but Jaka Tuszek, and some of the colleagues in the US. So what we know is there is not the perfect material for the elastocaloric application, because everybody builds a little bit different machine, it has different load cases, different elastocaloric regenerators, and we see that there needs to be an iterative feedback loop between material producer or material developer and machine designer, so that we can get better and better elastocaloric machines. So what are the requirements for elastocaloric materials? Where in actuators, we use heat to, or we transform heat to mechanical work. In the elastocalorics, we do the other way around. So we put some mechanical work into the material, we deform it by some means of mechanical machine, which might be a linear drive or hydraulic piston, whatever. So we deform the material, and that might be in tension, compression, might be torsion, might be bending. And then we release this mechanical work and use the entropic or exothermic or endothermic materials or properties of the transformations of the martensitic transformation and the backward transformation. So we use mainly pseudo-elastic material. And if you look at the literature, you see some requirements being put on the material. And what you find there are mostly mechanical and thermal requirements. And they are mostly based on the behavior of the material at room temperature. And from that, you calculate a COP, or coefficient of performance. And then you see on the small letters, material. This is still not the COP of your whole machine. You can have a very nice and very good material and still build a shitty machine that doesn't give you any cooling power at all. But we know that with a shitty material, you will not build a good machine. So mechanical requirements are the geometry. Do I have a thin wire? Then I have a good ratio of volume on surface. But I might have difficulties in putting that under compression. What about the functional stability? So does it hold for the number of cycles that are needed? And I want a small mechanical hysteresis because then I have more, let's say, a higher frequency that I can cycle it with. Thermal requirements are that it needs to be austenitic. And here in the literature, you find mostly the requirement of being austenitic at room temperature. And we will see later that this is not enough because room temperature is only for one condition. But if you want to put it in a car, there's no room temperature. Then we want a small heat capacity and high latent heat so that we have a high, what we call the elastocalorics, high temperature lift, be it to heat or to cool in both directions. What we want is a high latent heat so that with each transformation we get a good heating or cooling power. So what we don't see is we see nice alloy screenings, but we really don't see how someone manufactures semi-finished products out of that. We don't see requirements for the lifetime because that was all a lot of fundamental work and nobody thought about a real-life application. How many millions of cycles does my machine have to be performing between two maintenance cycles, for example? Then we have what I just said, changing ambient temperatures. If you have a refrigerator in your home, I would agree that the ambient temperature is mostly constant. You might have it a little bit warmer in the summer and a little bit colder in winter. If you are in the United States, then you will have it always really cold in winter because your AC is going full power. And then we have things like cost. Do I put in some expensive elements or not? The load case is really important. So these are all questions that we try to answer in the iterations with the elastocaloric regenerator groups. So let's look at some of these points. Functional stability, small mechanical hysteresis, and austenitic at room temperature. So we as material developers, we look at some points and try, okay, how do we achieve this? And for example, everybody knows that in NiTi, if you want to decrease your phase transformation temperatures, you can just increase the nickel content or the night to Ti ratio. And then if you are above 50.0 in atom percent, then the phase transformation temperatures will go down. Your standard medical nitinol is nickel-rich nitinol with 50.9 to 51 atom percent of nickel versus the rest of the balance being titanium. Then as you produce your alloys, you might have some precipitations. The temperatures might be prone to change again. If you do some heat treatments during your processing route, the temperatures can go up a little bit. So that's a non-stoichiometric system where you can control your phase transformation temperatures, but it's not really that simple. For the elastocaloric community, the standard nitinol for the medical industry works for demonstrators, but does not really work for really good elastocaloric regenerator systems. That's what everybody says. Why did you use nitinol? because that was the only thing that was available when I looked at the common supplier of nitinol, and we try to change that. One thing of NiTi is also that it has a rather large hysteresis. How do we get the hysteresis small? By adding copper. This is also nothing that we invented. That's been in the literature since the 90s. But then if you look at the literature, then you learn that if you put in a lot of copper, your material gets brittle. So you get a good functional stability because the crystallographic compatibility between austenite and martensite becomes better. And you see here, as you come over the threshold of, let's say, 7.5 atom percent copper, then you come from a B19 to B19 prime transformation to a B2 to B19 transformation. So this is where the hysteresis gets really small, but this is also where the material becomes really brittle. We have found a way to work this material. We can produce very nice materials which are B2 to B19 prime, and they have a small hysteresis. But what you also see is that the phase transformation temperatures are far from being pseudoelastic at room temperature. So how can we now take this small hysteresis material and decrease the transformation temperatures? We add a fourth element, we call it X, and these are elements that are between nickel and titanium in the periodic system of elements. So that would be vanadium, chromium, iron, and cobalt. And you might argue that manganese is missing. You don't want to put manganese in your vacuum induction furnace because it evaporates and it messes up your whole furnace and you have to clean for hours. So that's the first thing I learned from Jan Frenzel. Never put manganese in our furnace. That's why I didn't look further into this. You see that if we do this with NiTi copper, and we have done this for several copper contents on the B2 to B19 prime side, but also on the B2 to B19 side, what you see here are results of copper 10. The curves look more or less exactly the same for copper 5. Just the hysteresis is bigger. So we can play with the copper content for having a larger or a smaller hysteresis, and we can put in these elements for reducing or for fine-tuning the AF. Of course, this is just if we want to have an AF of 0, then I can do some interpolations, and then I know where how much of these elements I have to put into. If someone comes and wants a higher AF, I can do this as well, of course. What we found out is that putting in iron and cobalt, which substitute nickel, they provide a very good workability, but the functional stability becomes very poor. So we went with vanadium and chromium, and these are now very good candidates for not only for elastocaloric applications, they are also our main alloy systems for thermostat valves in actuators for the automotive industry. But they are also very good candidates for elastocalorics. Now, we have AF of 0, that works really fine. We have a small hysteresis, which is good. Does it really work in mechanical? And here you see some curves, and the answer is yes. And we can learn a few things of these curves. So we compare here a binary NiTi nickel 50.7 alloy with an NiTi copper vanadium basis 5 and basis 10 atom percent copper. And what do we learn? So these are all samples of 20 mechanical cycles. And what we see is that the binary sample starts with a very high upper plateau stress, and it fatigues very much. And you see here the difference between the first and the second cycle is really big. And then it goes into some kind of saturation, which you can do as a training process, yes. But you see that the hysteresis remains rather large. Then we go to a quaternary system with 5 atom percent copper, and we see that the functional stability, which is the loss of upper plateau stress and also the accumulation of residual strain after mechanical cycling, is reduced significantly. And then we go to the copper 10, which would be B2 to B19. You don't see, or you almost don't see any change. So the material is really stable. Why is it so stable? Because of the crystallographic compatibility. That's the GNTM, the theory of the geometric nonlinear theory of martensite, where we learn that the small hysteresis stems from a good compatibility between austenite and martensite and having a almost perfectly coherent, I don't know the word of that, the habit plane, that's it. But there's also one thing that you learn. You see the strain, which I can reach with the material with less copper and the strain with the material with 10 atom% copper. It's almost half. So you pay a price. The hysteresis is small and the functional stability is really high, but as austenite and martensite are so compatible, the transformation strain becomes smaller. And so you see that there's not one factor which determines if this is the best material. The best material needs to be the best material for a certain application. And there's no guarantee to say, okay, the red one is better than the blue one is better than the black one. We can have applications where the red one is the best, where the blue one is the best, or even where the black one is the best. So we always have to look on fine-tuning the material and customize it for a certain application. And this is where we need the feedback of our partners. Now, this alloy with the 5 atom% copper, vanadium, let's say, by coincidence, was deemed one of the most promising materials for elastocalorics. When I did this material, that was 2012, I just wanted to have a pseudo-elastic specimen. And then my successor, Andre, was sitting in my office after me. He just took this material and did his calculations for elastocalorics, and he found out that this material should have one of the biggest COPs of materials known in the literature. And then he put this to work. He compared this with some binary NiTi and did also some mechanical cycling. You see again here, there is some fatigue, there is some residual strain, even though depending on the heat treatment, on the condition, you can improve also binary material, you can stabilize it. But here you see almost no residual strain, which is really good. What is very important here is that the work output here is a lot bigger for the binary material. So the work required to do a full hysteresis loop is much bigger. This was during a research group with the Seeleke group, and they put this in their elastocaloric characterization machine. And what they found out was that the elastocaloric behavior of both materials were more or less the same. However, the work needed for the quaternary material was 4 times lower. So we get a 4 times higher COP, which until today makes it a very promising material. So we could say, okay, we're done there. We have made the best material. Of course not, because now somebody comes and says, I want to put this in a car, and my car goes from Alaska to Arizona, and what about the temperature changes? There's not much use in having something pseudoelastic at room temperature. And for those who know this, Nitinol is very nasty when you change temperatures because it changes its mechanical properties. We call this the Clausius-Clapeyron effect. And you see here, this were tensile tests, just quick and dirty with the same specimen, just changing the temperatures in the climate chamber from -20 to +75, so almost 100 Kelvin of difference. And you see that our upper plateau stress goes from 400 megapascal to almost 1,000 megapascal. That means if you build a machine frame where you want to put in your material as an elastocaloric cooling material, you would need to build it so strong that it can withhold these almost 1,000 megapascal. So here you would have a rather over-dimensioned mechanical system which needs to work with this sturdy big frame that can withhold 1,000 megapascal. And now your client from the automotive industry will tell you this needs to be as light as possible. And we don't want to have extra weight, because extra weight destroys our COP. So we're thinking about a method. How can we compensate this Clausius-Clapeyron? And one thing would be to look for alloy compositions which have a lower slope here, but it seems that it's not the case. So if you go to binary, ternary, quaternary, it's always almost in this region. So we have come up with an idea how to compensate this. So here we have, if we look at the delta T from 0 degrees to 75, we have a delta sigma of 400 megapascal. And an idea would be, if we can now come with different materials which are compensating for the Clausius-Clapeyron, we start at a lower first plateau stress, and then as we go higher with the temperature, the next material state kicks in. And this is how we could have a smaller delta sigma. And this is what we wanted to try out. And so you could, for example, for cascaded systems, buy material that starts here with a NiTi 50-50, then have a 54, then have a 51. Then in theory, you would have a cascaded system with different plateau stresses at different temperatures. However, in binary NiTi, the hysteresis depends a lot on composition. And if you look here and just on binary changing compositions, you do have a very different hysteresis behavior. For cascaded systems, that does not really work. What we want is the same mechanical behavior at different temperatures. And you look at the literature, there's a very nice paper out in Nature about an elastocaloric regenerator from Hong Kong, from Guangzhou. And I see, when I just look at the DSC curves, that this material was not customized. And they say it in the paper. They just bought 3 different materials from Kellogg's research lab. There's no material science going into this. These are not material scientists. They are energy people. They build an elastocaloric regenerator. So they just buy what they can get. And you see here, this material will definitely not have the same mechanical behavior. And we want to fine-tune the material so that we can customize this. So here we have a quaternary alloy, and we do different heat treatments, and we don't change the composition, and we look at the tensile curves at a different at a constant temperature. We look at the first cycle, which is what you mostly see when you see tensile curves, but we know that the material will change after some training cycles, and then we look at the 20th cycle. And now we have a different set of heat treatments, and we try to get these at different temperatures to have an overlay. That was our goal to show here in this work. So we said we wanted to look into what test temperature do we have to apply to have 300 megapascal at a 3% elongation, and to see if we can get this really constant. And so Alex spent a lot of time in the lab between heat treatment furnace and tensile tester and climate chamber, and this is what we got out. So we had a large program of heat treatments, and this is always the same diameter and the same alloy composition and different heat treatment parameters. And then we go to different test temperatures, and we achieve that they have all more or less the same mechanical response. And this is what we want for a cascaded system. So now you can have the same mechanical, let's say the mechanical frame for your machine operating at different temperatures. This is just a delta T of 20 Kelvin, but the methodology, we will increase this so that we can get up to 50, 70, 100 Kelvin, and always having a next material phase kick in so that the machine always works with the same mechanical conditions under different temperatures. So here again, you see different heat treatments, same compositions, and you have the first mechanical cycles at constant temperature, and then at the right one, you have different testing temperatures. Here in, I think, maybe you can step in, Alex, that would be 5 Kelvin steps that we did. Yeah, that was more or less what we wanted to show, that it is possible to customize materials. And here, was just one composition, and we can now have different heat treatment parameters. We can change the composition, and with this method, we can create material systems, material cascades for a very large temperature span, and that allows us to, well, allows our partners to build better elastocaloric regenerators. That's for now for the conclusion. So I already said, it's not just a material that you do in an alloy screening where you have a button melt and do a DSC. That's not enough. You need to be able to produce a semi-finished product out of that. Maybe a wire, maybe a strip, maybe a tube, maybe a bar, whatever the regenerator needs. So the heat treatment and training is very important. We almost never use first cycle data because we know that the material will change over cycles. We have changing compositions, we have changing parameters. Before we deliver out a spool of material or a batch of material, we want it to be trained. Then, as let's say a homework for the elastocaloric community, the requirements need to be refined. We need more data on that. It's not just enough that I want a material that has a high latent heat and has an AF of 0 degrees. So there is more to that. And we see that the idea was formulated on SMST in May. In ESOMAT in August, we showed it. So we are really picking up pace in the elastocaloric development. And so we want, and we are working together, as I said in the beginning, with most of the elastocaloric groups in Europe, so that we can really pick up the pace here. And we were just awarded a research grant, which is the biggest research grant in our history so far, which is SMA systems, cascaded elastocaloric systems for automotive applications. So we think that in the next webinar, the next conference, we will be able to show even more. Now I'm open for your questions.
Thanks very much, Burkhard, for the presentation. A lot of impressive work on different developments, so well done. Shall we take questions now, if that's okay? Maybe just open it up for the audience, and anybody has a question, please put it into the chat.
I think we already have the first one.
I'm still sharing. I can't see the chat, so if someone might read to me, that would be
I
okay.
can read it,
Yeah.
if you want. The first question coming from Charan, and ask you, I have a question that what was the shape of the material you use for extracting its properties?
That was, if I remember correctly, 200 micron wire in tension.
Mm-hmm. Maybe I can ask you a question, if you don't mind, until the other question arrive. What is your comment about the additive manufacturing of, let's say, shape memory material for using specifically for elastocaloric applications? Because in this case, we are dealing with the different type of, let's say, shape of the materials and also different manufacturing process.
We think that it's really promising because you can, with additive, you can do, let's say, exotic structures, things that would have a better surface to volume ratio, and you have a better heat transfer. However, you would also need to have very good surfaces so that the material can withstand a high number of cycles. So I think that it's really important to look into it, because otherwise we will not know. But it needs to be structures that are stable, let's say, against buckling. I don't see an additive manufactured part for a tensile application, but for compression, yes. And then you would need to improve it against buckling. But it's really interesting to have some sort of sandwich or foam or something like that.
There's another question just came in there on the chat, and it's a question around the brittleness of nickel titanium tertiary quaternary alloy. The question is, what would you consider as the factors? Why is the brittleness increasing? Is it precipitates? Is it grain size? Is the question? Yeah.
In stoichiometric alloys, let's say even in quaternary, if we replace the material, the nickel and titanium, so that we are always on the 50.0 balance, we don't see a lot of precipitations, or we don't see any precipitations. So the brittleness increases when you go to the B2 to B19 phase, and then it's just a brittle material. But we have learned that once you go past a certain point in refining the microstructure, then the material becomes ductile at one point. I see this in NiTi high temperature alloys. I see this in NiTi copper with 15 to 20 atom % copper. When you do the first pass of deformation wrong, it crumbles like a cookie. But if you do it well, then at some point it becomes really ductile, and you can put in a lot of cold work.
Thanks for that, Burkhard. There's no other questions, and I'm just looking at the time. We're at 34 minutes past 2, so maybe if we leave it there for the moment, if that's okay. Thanks very much, Burkhard. And moving on to the next presentation. This is Professor Marialaura Tocci from University of Brescia. She's a materials science and engineering expert, and in terms of her research area, and she's going to present on the heat treatment of nickel titanium alloy for biomedical applications. Passing over to you, Maria. Thank you.
Thank you for the presentation. Good afternoon or good morning or good evening to everyone. So I will discuss the study about the effect of heat treatments on superelasticity of nickel titanium alloy produced with an additive manufacturing process. This is actually a work group, and other university beside mine, University of Brescia, were involved, and especially this is the work of the results from the PhD work of a colleague of mine, Beatrice Bravi. So what are we talking about? We know that laser powder bed fusion is a process that is the most widely used and studied for the additive manufacturing of metallic materials. We also know that there are a number of studies dealing with the use, the exploitation of this technology to produce biomedical devices, or to investigate the possibility to produce biomedical devices with nickel titanium alloys, since as for instance stents or other endovascular devices, for instance, that exploit the possibility to produce complex geometries using laser powder bed fusion, and also the possibility to produce a prosthesis, a device which is designed according to the specific needs of the patient. This is clearly the objective. Still, there's a lot of work going on to achieve this goal, and especially related to stent, one of the first challenge to overcome is to optimize the superelastic behavior. Besides the optimization of the chemical composition of the process parameters, it is fundamental to tune and optimize the heat treatments in order to achieve the desired superelastic behavior. This is usually carried out applying a two-step heat treatment involving a first high-temperature treatment, usually indicated as solution treatment, followed by an artificial aging. But on the other hand, it is possible to exploit the microstructure that we obtain after the manufacturing process, so after the powder bed fusion, which we know is already a supersaturated solution due to the high cooling rates that we achieve during this process. So the question is, why not to skip the solution treatment and apply directly aging after production and see if we can achieve and we can tailor and achieve the superelastic behavior that we want. There are a few studies working on this topic, and therefore there's still work to do in order to understand if it is a feasible and way or not to solve the problem. So we performed our experiments on cylinders that were provided by Dublin City universities that took care of all the manufacturing process. You can see the size of the specimen, and you can also see a picture of one of the cylindric specimens. We have some data about the manufacturing process, and as you can see, we use a nickel-rich powder to produce this sample. Focusing on the heat treatments that are the key point, let's say, of this study, you can see that we compare the two different approaches. So we perform both solution treatments followed by aging, and in this case we carried out a solution treatment at 950 degrees for 5.5 hours, followed by two different aging treatments. So a first aging at 400 degrees for 15 minutes, and a second one carried out at 500 degrees Celsius for again 15 minutes. On the other hand, we compare the results that we can obtain applying instead a direct aging with the same parameters that we used for for the previous treatments that I mentioned. We indicated with S the samples that were solution treated, and with DA instead the samples that were direct aged. Also, the choice to apply of a short aging treatment was set in order to investigate if we can even shorten the time of this aging treatment and make it faster and more cost effective. The characterization carried out is listed here. So we perform DSC analysis to investigate the transformation temperature. We perform a microstructural characterization with optical and electron microscopy, and we then investigated the superelastic behavior using compression tests under different configurations. So we perform cyclic test up to 6% deformation with 15 cycles at different temperatures. So room temperature, 37 degrees Celsius to reproduce the body temperature, and in order to compare materials in the same thermodynamic state at a temperature that's 10 degrees above the austenite finish temperature. Then we perform incremental compression test up to 10% strain, in this case only at room temperature. And from the results, from the curve from this test, we calculated the maximum stress reached, the pseudoelastic stress as the critical stress that induced the martensitic transformation, and the residual strain. Finally, in order to build the stress temperature diagram, we needed also to perform test up to failure, and in this case, temperature was set at room temperature 150 degrees, selected these high temperatures was selected simply to be able to build the graphs that is similar to what we can see here, so a stress temperature diagram, in order to identify which is the superelastic window for the material after the different heat treatments. So if we consider the definition, the identification of the transformation temperature, here we can see the thermograms for the S-bill sample, and as you can see, we identify the martensite to austenite transformation at a temperature well below the room temperature. But what happens after the heat treatments? All the heat treatments applied were able to shift the transformation temperature to higher values. So this is evident for all the heat treatment that we tested, and it is also evident if we compare the heat treatment with and without the solution treatment, but the same aging treatment, that the curves are very similar, if not superimposable. And this was a first hint that actually the solution treatment could be a step that could be avoided. This is especially evident for the treatment carried out at 400 degrees. Then it was also possible to observe that for almost all cases, as compared to the S-bill condition, the transformation is not a single, does not take place in one step, but in two steps, since we identified the formation of an intermediate phase indicated as the R phase, which suggests the formation and the presence of nickel 4 titanium 3 precipitate. So it is known from the literature that the presence of the R phase is enhanced, let's say, by the presence of these precipitates. So these were a further indication that the heat treatments tested were effective in shifting the transformation temperature and in creating and in allowing the formation of these precipitates. Considering instead the microstructure under the S-bill condition, we can observe a conventional chessboard-like structure with islands inside the square, and a homogeneous matrix can be identified, while after the heat treatment it was possible to observe the presence of some martensite grains that are highlighted here with yellow circles or arrows, and that can be better appreciated in these images at higher magnification. So according to what we found from the DSC analysis, we have at room temperature after heat treatment both austenite with a limited but still evident presence of martensite. Moving to the mechanical characterization, here you can see the stress strain curves from the cyclic compression test carried out at room temperature. It is evident if we compare the behavior of the material after heat treatment with the behavior under S-bill condition that the superelastic behavior improves after the heat treatment. And also it can be appreciated if we again compare the heat treatment considering the option with and without, the alternative with and without the solution treatment, that again we found almost superimposable behavior, so similar, extremely similar behavior, again suggesting that solution treatment, it does not play a fundamental role in determining the superelastic behavior of the material. This is further confirmed if we have a look at the data of stress and residual strain for each cycle, and especially if we have a look to the residual strain after all the experiments, it is evident that after heat treatments, this residual strain is much lower as compared to the as-built condition. So in any case, the treatments are effective in improving superelastic features. Similar results were found after incremental compression tests, and in fact, here we can see that we have again very similar behavior for heat treatments carried out with and without the solution treatment. And if we compare the behavior of the material before and after the treatment, again, we can recognize an improvement in the superelastic behavior of the material after the heat treatments selected. In particular, we also see that the higher the temperature of the aging treatment, the lower the pseudoelastic stress and also the maximum stress. Considering the residual strain here, again, and it is also evident from the curve that we have a residual strain that is much lower after heat treatment. So this is a parameter that is strongly improved. Moving to the test carried out at 37 degrees Celsius, we can observe that we confirm basically what already observed, so improved superelastic behavior after heat treatment and minor lower residual strain at the end of the experiment after the heat treatment. On the other hand, when we test the material in more or less the same thermodynamic state, so we place our material in a condition that is what we can find 10 degrees above the austenite finish temperature, so we test carried out at different temperature for each material, for each condition, we can see that the as-built sample put in the correct condition exhibits a superelastic behavior, even though in any case samples after heat treatment perform better, and there's also an increase in stress with the increase of the temperature. So, putting together all the data we obtain from DSC analysis to identify the transformation temperature and the critical stresses measured from the cyclic compression test, we were able to build for each condition this stress temperature diagram. As you can see, so for each condition, we can identify the superelastic window, and it is possible to observe that with the heat treatment, we have an increase in the critical stress for the slip deformation, and instead a decrease in the pseudoelastic stress, and an increase, as we said, of the transformation temperature. This results in an enlarged superelastic window. Again, something positive if we consider the application we have in mind. This enlargement is particularly evident for treatment carried out at with aging carried out at 500 degrees. To better understand the reason why this effect of the treatment, this material response to the heat treatment, we more deeply characterized the microstructure. So we performed TEM analysis, and on which samples. We prefer to carry out this investigation on the two conditions that for us are more relevant, so the two direct aged conditions, the one at 4 and the one at 500 degrees Celsius. In both cases, we can observe the presence of these, let's say, mixed structures. So we have austenite, we have martensite, as already mentioned, and from diffraction analysis, it was possible also to identify the presence of the R phase, the one that we inferred from the results from the SC analysis. Comparing the two treatments, it was found that after the DA400 treatment, there's a higher amount of martensite in agreement with the results from the SC. While if we increase the temperature of the aging, we have a higher amount of the R phase, this intermediate phase, that we said usually suggests the presence of precipitates, of nickel-4 titanium-3 precipitates that were actually observed. As you can see in these images, they have a lenticular shape, and as you can see also from the diagrams, comparing these precipitates and their distribution in the samples after these two aging treatments, we found more or less a similar size distribution and a similar average size, but these precipitates were much more abundant in the sample treated at 500 degrees, indicating that the higher treatment is actually more effective in promoting the formation of these precipitates and in agreement with the more abundant R phase, as we said. So, which are the contribution of these precipitates? They play a fundamental role in enhancing the superelastic behavior, because the formation of these precipitates causes a loss of nickel in the matrix that is responsible for the increase in the transformation temperature. They are also nucleation sites for the martensite formation during the formation, and therefore they contribute to reduce the pseudoelastic stress. And on the other hand, they harden the matrix, strengthen the matrix, contributed to increase instead the critical stress for slip deformation. So, to conclude, we have an improvement of the superelastic behavior after all the heat treatments carried out. This was demonstrated by the widening of the superelastic window after heat treatments in the temperature range that is interested for biomedical application. This is mainly due to the formation of these nickel-4 titanium-3 precipitates that, as we can see, contribute in different ways for this enhancement of the superelastic behavior. This was found true for all the treatment analyzed, so also the, let's say, innovative one, the direct aging treatment carried out for a short time. It was 15 minutes treatment, indicating that more interest and further studies can be carried out, since this seems an interesting approach for potential biomedical applications, and that, as we said, we can work on it treatment that skip the solution annealing step, also in order to reduce the treatment routes, make it more sustainable and cost-effective. And with this, I conclude. I leave here some contacts of me and my colleagues, and maps showing where's our city, our university is placed in the north of Italy. So thank you again.
Thanks very much, Marialaura. A great presentation. So maybe we're give opportunity for people to type their questions into the chat, and while we're waiting for that, maybe just a question around the residual stress that you presented some data on the residual stress. Was that measured by XRD, or what technique did you use for measuring the residual stress?
No, it's the residual strain. Sorry, maybe I used the wrong term. It was only the residual strain after the deformation, not the residual stresses.
Yep. Okay. Yep.
Maybe it was my mistake.
So it looks very promising in the sense that you can now do a heat treatment as an aging heat treatment. Presumably that would be quite good at relieving a lot of the residual stress as well, even at the 400, 500 degrees Celsius range for a short time, and then achieve good properties for stent and biomedical applications. I think we have a question. I have a question regarding the heat treatment. So the question is regarding the heat treatment, specifically the solution heat treatment and direct aging. Could you please elaborate on the details of the furnace and the gas supply setup used during the annealing process, is the question.
Okay, yes, we perform the heat treatment under vacuum. So we used an industrial furnace in order to ensure the correct condition to avoid the oxidation of the samples. So we actually asked the support of a company that build this kind of furnaces in order to be sure that we carry out the experiment in the correct condition.
And there's Andre has asked a second question. Thanks, Andre, for that question. Another question has come in from Alexander Paulson, and the question is: did you look at the texture for the?
We are working on it. Actually, we are going to perform a BSD analysis because this was a point that we wanted to investigate, and we consider that we tested sample built always in vertical conditions. So if there's a texture, the contribution should be the same for each sample, but we are going to investigate it.
Burkhard, you have a question there. Did you use water quenching is the question? Yeah.
Did you have also water quenching? Yes, we tested different cooling rates. So we perform experiments cooling air and water, and finally we found that quenching in water is a better solution.
Another question, Pushkar.
Then the sample were machined, so in any case, for testing. So in any case, the surface finishing was not the one of the as-built, of course.
And another question, Pushkar has asked, did you study the influence of residual stress on phase transformations?
No, actually, no, this is not something that we considered for this kind of study.
So the results of the different heat treatments were seen in terms of the DSC and their effect on the phase transformations, but not directly the residual stress measured from a quantification perspective.
Yeah. If I said residual stress, it was my mistake. I meant residual strain.
Any other questions from anybody with a question into the chat? Not at that point. So because we've come up to the 3 o'clock mark, this is perfect timing. Well done, guys, in terms of keeping your presentations perfectly timed. Maybe one last question. Sharan has asked, did you face any oxidization while carrying out the heat treatment? If yes, how did you overcome the issue?
Okay, well, consider that in any case, we machined the sample before testing. So even if there was a slight oxidation on the ex-built surface, we are quite sure to have removed it when we tested the sample. But sure, to carry out the treatment without oxidation is always tricky, and a point to bear in mind.
Okay, I think that's it for the time slot that we have. So thank you very much to Marialaura Tocci for her presentation.
Thank you.
And Maria Beatrice, well done on all of the good work as well. And best of luck in the live.
And thanks, Beatrice.
Thank you also, Burkhard, Maaß, for your presentation as well. Yeah. I'll pass it back to Burkhard now, maybe to close out.
Yeah. Thank you very much, both speakers, and thank you indeed, Professor Brabazon, for hosting these two great speakers and chairing also this session. I just want to add one point, that the video of this session will be shared later on LinkedIn and also YouTube of this specific webinar. And that's all from me, and hopefully see you also in future in other upcoming webinars. Thank you, everyone, and have a great day.
Cheers, guys. Bye.
Thank you. Bye.
Bye.